after presenting how it works from the outside, I take the freedom to dive into it, right? The inside. So the goal is we have a bunch of hosts with a bunch of drives in it, and we're creating a highly available cloud storage solution. And what's in it? What's happening in the box? And this is my favorite diagram to explain the architecture. So here at the top, we have XCP-ng, and it interacts with the LINSTOR system. So there is a REST API, and there's also a CLI, so you can also type commands to see what's going on. And then we have here the LINSTOR controller, and as is illustrated here, the LINSTOR controller can run on different machines. So it is usually configured in a HA setup. This is also the way how it's configured in the XCP-ng context. And what else is here? So on each host that is part of the cluster, we have another component, that's the LINSTOR satellite. So the LINSTOR satellite runs on all of the machines. And it's used by LINSTOR to execute local actions, like creating logic volumes, placing their config file for DRBD, etc. And yeah, the LINSTOR satellite is a complete stateless component, so it doesn't store data itself. The LINSTOR controller that has the embedded database, it remembers who is part of the cluster and which storage resources, where they exist, etc. And all what we see here, that is just, let's say, the control structure. So what LINSTOR is doing. The actual data volumes, that are the DRBD volumes, they are independent from this control structure after they got created. So we need a control structure to create them, but then the data path is completely independent of this control structure. So that means a failover doesn't affect I/O in a running virtual machine at all. It would even be possible to upgrade LINSTOR itself while VMs do I/O to the virtual volumes. Now, let's dive a little bit deeper. And when we look at an example cluster, and let's say this is a setup of 6 hypervisors, so 6 XCP-ng nodes, and each of these nodes has built-in storage devices, maybe NVMe drives, right? And there was a pool created that spans all the 6 machines with NVMe drives from all of them. If the system needs a new virtual volume, LINSTOR gets with the request where the volume will be accessed, and it tries to place one of the replicas. It tries to co-locate one of the data replicas with where the VM will initially run. So we have here the orange VM, one replica of its virtual disk, and the second replica of the virtual disk. Same with the black one. And of course, we can migrate a virtual machine. If we migrate the black VM to this hypervisor, we get DRBD into what's called the diskless mode of operation. So here the VM is accessing a virtual block device, but all the reads and writes now need to be shipped over the network. And as was already pointed out, you better have at least a 10 gigabit network or better, 25 gigabit, 100 gigabit to support that. And I also want to mention, while this is possible, it's of course not the optimal layout, right? Because the Orange VM has the advantage that read requests are carried out locally without creating any network traffic and without adding network latency to the read requests. The Black VM has in that regard a small disadvantage. But sometimes that's acceptable, and you enjoy the flexibility of moving VMs around with accessing their storage replicas remotely. And it's possible to configure LINSTOR to automatically migrate storage with the workload. So if that is enabled, LINSTOR would check after a certain time. Let's say you said in this policy, after it moved for an hour, LINSTOR should check, okay, if there is enough space available. If it is, it creates a new replica on the host where the VM is running. Then DRBD will replicate all the data over. And after that is finished, LINSTOR checks its policy again and sees in the policy, oh, this virtual volume should be two-way redundant. So it will then remove, let's say, this replica since 2 are enough. So I hope these examples gave you an overview how this system works. And now let's go a little bit deeper into the data path component, which is called DRBD. So DRBD creates, so you know the host operating system on these hypervisors is Linux. So DRBD is a device driver that provides you virtual block devices on Linux, and they happen to be replicated. And these virtual block devices, they are available probably on multiple hosts. And in the moment you open it for reading or writing, so this is the some Xen process. Sorry, I don't know exact the details. It opens it, and at that moment becomes promoted to primary. And with that, the direction of replication is defined. And if all the software layers above us terminate this process here and start it somewhere else, then this automatically demotes to secondary, and the other guy promotes to primary, and the direction reverses. The system is also capable of replicating multiple volumes within a single logical replication stream. That's so-called consistency groups. That's useful if you have physical storage of different properties and an application spanning spanning at least two of those storage types. As we already saw in the demo, it can do two replicas or three or more. The upper limit is 32, but nobody needs that. Each of the replication links can be synchronous or asynchronous. You can switch that at runtime. So asynchronous replicas allow you to have replicas in a greater distance, right? Outside of your primary data center, of your main data center. And I think what we already saw very briefly in the live demo is it can allow your VM to run on a hypervisor where no physical copy of your data exists. So we call this a diskless mode, or the a node operating in diskless mode for a specific resource, and it might be primary there. And also, of course, DRBD shields you from any IO errors. So if the VM is executing here a read request, and let's say DRBD decided to send it to this storage node, and the storage node fails while it should answer the read request, right? Then this node would recognize it. Oh, there's no answer coming back, and the TCP connection died. Then it would reissue the read request to the other node, get the data, and deliver it to the application, deliver it to the VM. So the VM doesn't see a failing IO request. It just sees, oh, this IO request took a little bit longer, but it can continue to run. And if a failed node comes back, it automatically reintegrates with the cluster. So it gets an up. So DRBD does a resync from the surviving node to the node that was temporarily away. It copies over all the blocks that were modified in the meantime. And after that is finished, it's available again for the primary to execute read requests. Okay, so this is just another illustration to look at it. Again, I usually use this illustration to explain the difference between the synchronous mode of operation, and I think that's the default in XCP-ng, and the asynchronous mode of replication, where I might have here a longer distance. Okay, so that was for my overview dive from the live demo, bridging all the way to then the improvements Gabo will talk about. And yeah, this is one of my cheat sheets. I wanted to share that with you. So if your workload is very performance critical, it makes a difference if your VMs run where one of the replicas is, and you can either use the interface or here are the commands how to find out which replicas of your storage resources are and where the VMs are located. Okay, that's it from my part. And I hand back to RT.
Very good. Thank you, Phil. And we did have a question come in here on YouTube. And the question is, for you, Phil, can you describe how the diskless to diskful DRBD migration works internally and how it might or might not affect VMs that are accessing the device?
Diskless to diskful. Oh, okay, yeah. So this was on the slide where I explained that after a certain time, or you can configure LINSTOR in a way that after a certain time, it tries to migrate one replica to the machine where workload is running. Yeah, so in DRBD speak, that's a resync. And it will, of course, use a certain percentage of your storage bandwidth. And you can also limit that. So during the process, your VM might notice, let's say, a bit reduced IO performance or higher IO latency because the IO subsystem is busy in copying over all those blocks. But after that, it will see better performance.